So welcome all of you in the second video of electromagnetism. In the previous video, we discussed about Oersted experiment and right-hand thumb rule, and we discussed even the properties of magnetic field lines. So now in this video, we will be discussing about magnetic field due to current in a loop. We'll be discussing about clock rule. We'll be discussing about electromagnet, permanent magnet, temporary magnets. And we'll also be discussing about the similarities, dissimilarities, advantages and disadvantages of permanent magnet and temporary magnet. And we'll also be talking about ways of increasing the magnetic field of an electromagnet. So let's start with. So the very first thing is the circular loop. So we have a circular loop, right? And again, we are going to have magnetic field here, a loop, magnetic field here and here, right? And we are going to have right. So what it is representing. Now how to find out from which direction to which direction the magnetic field lines are going to run? So if you see here, current is moving from here. It means current is passing through here. So the magnetic field lines, they are going to encircle like this, right? It means they are going to move this way. You just check out, just consider this figure and you just curl your fingers. You have to have your right hand, use right hand thumb rule, right? So this is how they are going to behave, right? So from here to here, they are going to move. And same way, if you apply right hand thumb rule here, they are going to move this way. And what about this? I have marked a line here. What it is representing? Actually, the effect is going to be cancelled here. So nearly parallel lines we are going to have here. It means the magnetic field lines are going to be uniform here. It means the intensity of the magnetic field lines, they are going to be same. The magnetic field is going to be same in these lines, or you can say in this area. So this is for circular loop. What about, this is one coil. What about if I just arrange such type of coil number of times? It means I'm talking about solenoid. So let's see how we are going to work on. So now we are going to talk about cylindrical coil or a solenoid. So what is a solenoid? If a conducting wire is wound in the form of a cylindrical coil, this is wound in the form of a cylindrical coil whose diameter is less in comparison to its length. See here, diameter is quite less as compared to its length, right? The coil is called a solenoid and it looks like a helical spring. So what is a helical spring? You must have seen your ball pens, right? So if you have seen the ball, the riffle is inserted in a helical spring. So that is the shape, helical spring, right? So how to find out the magnetic field in a solenoid? Let's see. For that, again, now when current will be passed through the solenoid, see here, when current will be passed through the solenoid, right? Again, this coil is going to behave like a magnet, right? So when it will start behaving like a magnet, there is going to be a magnetic field around this coil. So what sort of magnetic field it's going to have? Let's see. So it's basically going to have magnetic field here, right? And it's going to have a magnetic field here as well, right? This way. And in between, it's going to be like this. Parallel field lines are going to be there. So what actually these parallel field lines they depict? They actually depict that the magnetic field is going to be uniform here, right? And these circular loops, again, they are going to depict the magnetic field. Okay, but as we know that the magnetic field lines, they run from north to south, right? But how to get here? How to have north or south pole here, right? So for that we will be using a clock rule, right? So what is that clock rule? Clock rule is If current is flowing in anti-clockwise direction, then that pole is going to be north pole, and if current is going to be in clockwise direction, that side is going to be the side facing you will be south pole. So I'll be discussing it in just a few minutes later. But first of all here, so when you have a circular coil, we find the polarity by using, or you can say we find out the poles or the magnetic field lines using the clock rule. But when you have a straight conductor, straight wire is there, or a straight conductor is there, and suppose current is flowing through it, then how we find the magnetic field? We find magnetic field using right hand thumb rule. So it's a circular coil, right? So we will be finding out using clock rule. So just remember this, we will be discussing, right? And now what about suppose I increase the number of turns, what will happen? If I talk about the strength of magnetic field, how it's going to vary? So the strength of magnetic field, it actually depends on, it's going to increase if current is going to increase, right? And if current is going to decrease, strength of magnetic field is also going to decrease, right? What other factors could strengthen the magnetic field? How to increase the current? By increasing number of turns. Which turn I'm talking about? I'm talking about these turns. If the number of loops are increased, automatically there is going to be increase in the current, which will strengthen the magnetic field, right? And what else can be done? As I told you, it will start behaving like a magnet, right? So if I change the terminals here, means suppose this is your negative and this is going to be positive, right? So automatically there is going to be change in the direction of current also, right? It's going to be this way. Then what about the polarity? The polarity is also going to change. It means the magnetic field lines that are running, they are also going to change. Why they are going to change? Since these terminals have been changed, the direction of current has changed, automatically the polarity is going to change. Right? Strength is more here. It means it is more here. It means the strength, the magnetic field is stronger here. And as we move away, these lines will start becoming parallel, right? These will become parallel. So it means the strength is now uniform here. The strength of magnetic field is uniform here, right? It is maximum near the poles and it goes on decreasing as we move away from this this coil, and this coil is behaving like a magnet. It has become electromagnet. How come it has become electromagnet? Because we are using electricity to make a magnet. So this electricity is responsible for this. It means if I switch it off, no longer this coil is going to behave like a magnet. It will be a wire. A helical spring like structure will be there, that's all. It will not behave like a magnet till I switch on the current, right? So now let's talk about electromagnets in detail. So for a straight conductor, that is for example like a straight wire is there, how to find out the direction of current? That is by using right hand thumb rule. But what about the circular loop? How to find out in a circular loop from which part is going to be north pole and which part is going to be south pole? For that we have a clock rule. So what is there in the clock rule? For clock rule you have to look at the face of the loop. If the current around that face is in anti-clockwise direction, the face has the north polarity. But if the current at that face is in a clockwise direction, the face has the south polarity. So I'll give you a demo. Like see here, you have this, right? And coiling is there, right? And suppose now current is flowing from this direction. Current is flowing from this direction, right? When current is flowing in this direction, it means anti-clockwise current is flowing. So if it is anti-clockwise, right, it is going to be north pole. And if it is clockwise direction, if it is clockwise, then it's going to be south pole, right? So like we were talking about a solenoid. So in a solenoid, this is a solenoid, right? If clockwise direction, in clockwise direction current is flowing, then, oh, I should face, okay, clockwise, this way, suppose conductor you are placing it, this is a solenoid. And if now current is flowing in this direction clockwise, then this part is going to be south hand and this part is going to be north hand. And suppose it is opposite, that from this direction to this direction current is flowing, this direction to this direction. When I'm saying this direction, it means it is anti-clockwise. When it is anti-clockwise, right, the end that is facing you of the loop is going to be north pole and the other end is going to be a south pole, right? So we need to understand where to use clock rule and where to use right hand thumb rule. I hope so you people are clear now. So now let's define electromagnet. An electromagnet is a temporary strong magnet made by passing current in a coil wound around a piece of soft iron. So it is an artificial magnet, right? So we have two types of electromagnets. We have I-shaped. We will be actually discussing about two, but we have a number of, and U-shaped, right? So we have I-shaped electromagnet or bar magnet, we also call it, and the other is U-shaped or horseshoe. This is known as bar magnet and this is known as horseshoe, right? Horseshoe. So how to make it? So if you ask, is it there in the syllabus? See, bache, they'll not ask you. Yes, they may ask you to draw I-shaped electromagnet or bar-shaped electromagnet. And sometimes they give you question regarding, they simply give you a diagram and they ask you to find out the direction. They ask you to find out the poles, in which direction they will give you the direction of current and they may ask you in which direction the pole is, or vice versa. They may give you pole and they may ask you mark the arrow or mark the current in which it is direction it is flowing, right? So now first of all we'll be talking about I-shaped. So suppose this is your I-shaped, a soft iron core is there, right? And then you have battery, you have a key, and then you attach it with this, right? Now you are just going to make a winding. It's on the other side it's going to be this, again this, again this way, right? This is how it's going to be, right? And this way, right? So now from which direction to which direction current is going to flow? Current is going to flow from this direction. And when it's going to flow this way, underneath and this way, under and this way, this way, this way, right? Now if I hold, I consider this as an electromagnet, and if current is going in this direction, I mean to say this is clockwise direction. If you see my finger, right? Suppose this is a coil and if you see the direction of current, it is this way, clockwise, this way, right? And if it is clockwise, it means what about the polarity at this end facing me? It's going to be your south end, and the polarity that is on the other side, it's going to be your north polarity, right? So such type of question they may ask you. So this is your I-shaped or bar-shaped electromagnet. Next is your horseshoe magnet, and for that you have a horseshoe. This way you can have it, right? And you need to actually draw a U-shaped, right? Now again, this is from here. Suppose you attach a wire, you have a battery here, then you have a key here, right? And then you attach it with the wire here. Automatically wires are going to be this way and this way. Now how to arrange them? So if it's going to be this way, right, then it's going to be this way, it's going to be this way and this way, and then it's going to be this way, right? And it's this way, you can say, right? And then it's going to be this and this, right? So current is going to flow from here right? So again, it's moving in this direction, right? It's going to move from here till here till here. Now, the only thing that you need to take care is when current is moving in this direction, on the other side, it's going to be in the opposite direction. It means here and here, always the current will be marked opposite, right? And when it will move this side, it will come out to be like this, right? Now, if you see here, if you apply the clock rule, this side will come out to be south and this side will come out to be north. So this is your horseshoe or U-shaped electromagnet, right? So they may ask you where you are using these. So a bar-shaped electromagnet it's commonly used in switching devices, right? So these are used in switching devices, right? Switching devices to switch on and off, where in relay. And where relay is used, it is basically used in substations or power stations, right? And next is they may ask you, where are you using horseshoe magnet? So the very first thing that will that's going to strike your mind probably is the electric bell, right? So the electric bell you can write down. It is the electric bell where you are going to use it, right? So mostly such type of questions, 1 or 2 mark questions are there. It may be DC motor or AC generator is there, or your electric bell. In such type of gadgets you use your electromagnets, right? So now we are going to discuss how can we increase the magnetic field of an electromagnet. So if you see here, if I increase the number of turns, current is going to increase. How to increase the current? Vice versa, to increase the number of your loops. Now let's talk about permanent magnets. So what are permanent magnets? A permanent magnet is a naturally occurring magnet, right? Since it is not strong enough, that's why we had the need of electromagnet, right? So do we have some benefits of your permanent magnet over temporary or vice versa, right? So we have now permanent magnet, and we need to talk about the material also that is being used for temporary magnet and permanent magnet, right? So first of all, we need to understand permanent magnets, right? They are made up of steel, right? And it produces a permanent magnetic field. So the magnets, the ready-made magnets that we buy, we can't increase or decrease the strength of that magnet, right? Sometimes when we break the toys, or sometimes we find even you have your your audio boxes and all that. There you can take out the magnets, and if you see those magnets, you can't increase or decrease the strength. That is your permanent. That is permanent strength. Of which strength we are talking about? Of the magnetic field, right? You can't increase or decrease the strength. And since you can't change the strength of the magnetic field, okay, so the use of that magnet becomes restricted. And the polarity of the magnet, it can't be changed, right? So you have a fixed polarity, north and south, it's going to be fixed, right? And it cannot be easily demagnetized. Can't be easily demagnetized. Demagnetization is difficult. By the way, how can you demagnetize it? By heating it a very high temperature, or by damaging it by using a hammer. So with that, you actually change the alignment, and with the change of alignment, loses its property and it gets demagnetized, right? So the next point is we can talk about the difference between the temporary magnet and the permanent magnet. Temporary magnet, right? So as we discussed about, this is I can use another color, right? So this is your permanent, this is your temporary, right? So for your permanent steel is being used, right? For temporary magnet, soft iron is used. Soft iron is used, right? So next point can be the polarity. It is fixed. Polarity is fixed, right? Whereas polarity can be changed. Can be changed. How can it be changed? By changing the terminals of the battery, right? The strength is fixed. Strength is fixed. Whereas the strength can be increased or decreased by decreasing or increasing the current, or I can say by changing the number of turns in the loop, right? And next is, since you can increase the strength, automatically the strength of the magnetic field is also, this is going to remain same, whereas the strength of magnetic field can be changed, increase or decrease. You can increase or decrease, right? We discussed about demagnetization. Demagnetization of a permanent magnet is quite, it's a process that you need to have, to take it at a very high temperature, as we discussed earlier. Whereas for temporary magnet, it's quite easy. I'm talking about permanent magnet. If I'm talking about, I hope you understand, I'm talking about electromagnet. It's a temporary magnet, right? So they may give you differentiation between similarity or dissimilarity between temporary magnet or permanent magnet. Instead of temporary magnet, they can write electromagnet as well. So you need to understand it is actually one and the same thing. Okay, we were discussing about demagnetization. For electromagnet, its demagnetization is very simple. You have to simply switch off current. The moment you switch off the current, that soft iron piece, it will start behaving like a simple iron piece. And the moment you switch on the current, that soft iron piece will start behaving like a magnet, right? So next we can discuss about the, no doubt we have discussed the uses also side by side. But once again, we need to discuss about the uses of the electromagnet. Or like I told you that the electromagnets, they can also be termed as temporary magnets, right? So we can say, they may ask you uses of electromagnets. So when I'm saying electromagnet, right? So the very first use that comes into mind is for lifting and transporting heavy iron scrap or girders. Like some construction purposes going on, crane can be used to pick a very big soft iron piece. Provide a current, it will start behaving like a magnet. You just take it to the place where iron or scrap is lying. You just take that into deep. All the metallic structure, it will stick to it, the metallic things. And then you take it to the place where you want to dispose it off. You switch off current. Now that soft iron piece will again start behaving like a simple iron piece instead of magnet. Now you can change the things. So for shiftings, you can say, right? Or shifting, right? Or like for scrap or for construction purpose, right? And other can be for loading the furnace with iron. Loading furnace with iron. Furnace with iron, right? So again, like in manufacturing units, you use these soft iron pieces. They start behaving like a magnet. When you switch on current, you just put the things, when you bring that soft iron piece near the furnace, switch off current, it will drop the things into the chimney and the things will be sorted out, right? And next is, it is being used for medical purposes. How can it be used? For medical purposes. If I say medical purpose, it's basically, I'm talking about surgery, right? So what happens in surgery? Suppose some problem is there, some accident is there, and surgery is going on. What will happen? They see, the concept is going to be same. The application may vary, and depending upon the application, the gadget is going to be sophisticated, right? It's not going to be crane. It's not going to be, huge things. When we are using it for surgery, the device may be very sophisticatedly designed, right? Depending upon the requirement, things are designed, but the concept remains same. There also, suppose you want to pick out debris from the wound, again a sophisticated electromagnet is going to be there, and that can be used in the surgery, right? And it may be in the use of scientific research, right? In the use of scientific research, we can use it, right? And we have so many actually. They are even used in many electrical devices, that such as you have electric bell, right, or telegraph is there. We discussed about this, like electric motor, microphone, loudspeaker, etc. and so on, right? Next is, sometimes they ask you specifically, like I told you electric bell is used. They ask you about the use, and they ask you sometimes why soft iron piece is used. Soft iron piece is used as an electromagnet because of its retentivity. It has a tendency to get magnetized and demagnetized quickly. With the result, it gives a good choice to opt it for a electromagnet, right? They simply ask you what sort of magnet is used. U-shaped electromagnet is used, or horseshoe. For horseshoe magnet, or to have an electromagnet, which material is used? Soft iron is used. Why soft iron is used? Because of its retentive properties, because it gets magnetized and demagnetized easily. So I think we have finished till the section A of the chapter, right? So I hope so you must have followed and gear up for the section B. And please, all of you, take care. It's a high crucial time. Stay safe, stay healthy. Bye-bye.